Now, after we've got that, if we're going to write this in a base E model, that just means we need to change this to a number that's base E. So it'll look very much the same, 12.01, but we're going to write this as e to the ln 0.93 to the t. Now that's in a base E model, but we can also go to our calculator and figure out what the natural log, this natural log, ln of 0.93, and write this as 12.01 e to the negative 0.073 t, roughly. So that's the exponential model. What is the half-life if this is a decay model, or a doubling time if it's a growth model? Well, this is a decaying. It's getting less and less. So we want to get it to be half of what it started to be. So I can put half of 12.01 here, or I can realize that this just has to be, or this has to be 1/2. So I have 0.5 has to equal, I'll just use the original here, 0.93 to what t? What t of these will make 0.5? Now, if nothing else, I mean, I could change this to e to the ln 0.5 equals e to the ln 0.93 t, this to this, which is what we did here. It's that number. And so that would have to equal ln 0.5. So I could go ln 0.5 equals negative, this is what that power is, negative 0.073 t. So I just take ln 0.5, close parenthesis, divided by negative 0.073, and I get about 9.5 years, because t was in years up here. I could also, as I said in class, we could solve this for t by just graphing that. Go to y equals and go clear, and go up here and go 0.5 and 0.93 to the t, x, and zoom 4. There's one, and there's the other, and it looks like it crosses just maybe right at the edge of the screen, or maybe off, so I better go zoom 6. That'll go a little further. Now they cross. Second, calculate the intersection of this side and this side when the two sides are the same height. Calculate the intersection. The blue line is one of them, the red line is one of them, and I press enter again, and it says it happens at 9.55. Close enough. Okay, number 2. So 25 looks like the power of 5, 125 is the power of 5, and that's 5. So I could do these all in base 5. 25 is 5 squared, and that would be to the 3x. 125 is 5 to the third, times 5 to the x plus 1. And here we multiply the powers, and we get 6x with a base of 5. And here when we multiply, we add the powers, and so we get x plus 4. Subtract x, and x equals, divide both sides by 5, and x equals 4/5 or 0.8. Page 2. Now they're not in this any common base number, so we probably should just decide, do we want to go base 10, base E? Those are the common ones in the calculator, or we could do base 3. I'm going to do base 10, let's say. So 10 to the log 3, that's another name for 3. 3 squared times 10 log 11, that's another name for 11 to the x minus 2, equals 10 log 4 to the x. So that's 4, that's 11, and that's 3. So I have, I'm going to look up the log of 3, and, not on there, so I can quit. Log 3 is 0.477. So I have 2 times 0.477, so times 2, and the power on this 10 would be 0.954, and times, and so I'm going to be adding plus log 11, which is 1.041, and I'm going to have that times x, 1.041x, and also times a -2, times -2, and I get minus 2.083 rounded, equals, and over here I've got log 4, which is 0.602 times x, because you multiply the powers there. So now I've turned this into an Algebra 1 equation. I will subtract 0.602 from both sides, x, .602. I was thinking about something. And then I'll add these two, which will be a negative number. Let's see. Negative 2.083 plus 0.954 is negative 1.129. So if I add it to the other side, I will have positive 1.129. So subtract that from both sides, add that to both sides, and combine them, and subtract this from both sides, and I get, see, 1.041 minus 0.602. I get 0.439x equals that, and so then I will divide that 1.129 divided by 0.439, and I get x will have to be 2.572. That should be close. I will do a check. So I'm going to type in, throw 3 squared is 9 times 11 to the 2.572 minus 2. And I get 35.47-ish. Now let's do 4 to the 2.572. And I get 35.35. Close enough. That looks like my process is right. I know these were rounded, and so I'm going to get an approximate answer. This says, to what power do I take 2 to get 8? I take 2 to the third to get 8, and times 4, which is 12. This says, to what power do I take 10 to get this? So that's going to be some number I take 10 to get that, and now I'm taking 10 to that power, so I am going to get 0.021. It's like the log base 10 and 10 with a base. These basically cancel each other. Same as this says, to what power do I take e to get e to the 9? Or you can say 9 comes down, and then to what power do I take e to get e, and it is 1 and times the 9. So this is 9. When you subtract logs, you divide, but we can't do that when there's a 2 on that and not here. So we've got to move the 2 up as a power. And I saw some people turning this in, saying they then write it as x plus 1, whole thing squared, minus log base 4 of x. If we get this to a single log, we can use the power, change the power to log, log to power rule. So now we're subtracting, so we're going to get log base 4 of x plus 1 squared divided by x. When you subtract, you divide. Now we have a log equation, single log equation, which we can rewrite as a power equation. To what power do I take 4 to get this? I take 4 to the 1 to get this. So I have 4 to the 1, which is just 4, equals x plus 1 squared over x. That's converting log to power equation. So then I multiply both sides by x, and I get 4x equals x plus 1 squared. To solve this, I'm going to have to expand this x plus 1, which is x plus 1 times x plus 1, x squared plus x plus 1, so that's x squared plus 2x plus 1 equals 4x. When you got a quadratic, you have to be equal to 0, so I'm going to subtract 4x from both sides. And so I got 0 equals x squared minus 2x plus 1. And then you can graph that. You can use the quadratic formula, or you can factor it to find out what makes it 0. X minus 1 and x minus 1. So that means x would have to equal 1. And then I need to check and make sure this doesn't cause negative here. 1 plus 1 is not negative, or 0, and put 1 in there, it's not negative, so 1 works. And I can also type in 2 log base 4 of 2 minus log base 4 of 1 and see if that comes out to be 1. B. We're adding now, and when the sum of logs turns into a product, so we get log base 6 of x minus 5 times x equals 1. I have it in a single log expression, so I change to the power expression. 6 to the 1 is x squared minus 5x. multiplying these, and then taking 6 to the 1 equals that. Oh, that's just 6. I subtract it since I got a quadratic, and we get 0 equals x squared minus 5x minus 6, which factors to x minus 6 and x plus 1. You can graph it. You can use quadratic formula, but anyway, that's what we're trying to make be 0, which says x would have to either equal plus 6 or x would have to equal negative 1 to make that 0, or 6 to make that be 0. And then we have to check for extraneous solutions. If I put 6 in here, that's plus, positive, and that's positive. 6 should work. Minus 1 in there would mean the log of a negative number. We can't do that. Okay. Carbon-14 dating. The amount left is equal to the starting amount e to some number times t. If 10 grams, that must be the starting amount, decays to 2.989 grams in 10,000 years, find the K. So this is the ending amount, which goes in for AT. The starting amount, A0, is 10. E to the KT, and that's 10,000 years for the T. So to solve for K, we can graph this and we can graph this and find out when they're equal. And let's just do that. We could also divide by 10 and find out when e to the k times 10,000 equals 2.89 divided by 10 is 0.289. But let's just see. I'll just do the first one. So 2.89 and 10 e to the 10,000 x, and x would be standing for the k. And we want to know when they're equal, so second graph, there's one, there's the other one disappeared. What did I type in wrong? Let's go zoom 4. E to the 2.9. Boom, 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 boom. Why am I not seeing that? Graph. E to the k times 10,000. I know it goes up pretty fast. Let's see. Oh, that's probably what it is. Let's zoom in. We're not seeing it here, but that should intersect. Let's go back to where we were. Zoom 4. They should intersect. This graph goes up real fast because of the 10,000. So we're going to go second, calculate the intersection between that graph and the other graph, and my guess there, and it says it intersects, although you can't see it on the calculator, it says they intersect when k, that's what we're solving for, that's what our x is, k is equal to negative 1.241 e to the negative 4, which means times 10 to the negative 4, which is negative 0.000124. And that's what K is. Now, if we did it with the other one, 0.29 whatever, and take the 10 off of here, and graph, still looks the same, but second, calculate the intersection, and it still gives me that same number. Now the other way I could solve this is, that's in base E, so I could write this in base E, and so I could say ln of point E to the ln 0.289 equals E to the K times 10,000. So this has to equal that. So if I type in natural log of 0.289, on a regular screen, ln of 0.289, and then divide that by 10,000, which moves the decimal place 4 places, we get that same number. If you started with 50 grams, so instead of starting with 10, if you started with 50 grams, E to the, and this is now still carbon-14, it would be negative 0.000124 T. How much would you have left after 100 years? So we put 100 in for T to find out how much is there after 100 years. So all we have to do is type that in. 50 E to the negative 0.000124 times 100. And we get, there would be 49.38 grams left. So in 100 years, it doesn't change much, 50 to 49. That's why carbon dating is not used for short periods of time, like 100 years. It's used more for like thousands of years. In fact, let's find out how many years it takes to go to half as much as it was. So if it's going to half as much, this part would have to be equal to a half. So we're trying to figure out when E to the negative 0.000124 times T equals a half. Half of what we started with. If we start with 1, now it's a half. So now we could again write this as ln 0.5, E to the ln 0.5, E to this, so the ln 0.5 has to equal negative 0.000124 T, and we just take ln 0.5 divided by that. So ln 0.5 close parenthesis divided by negative 0.000124, and the half-life is about 5,600 years. 5, 5, 8, and 9, and 90 rounded off years. About 5,600. Back page. You need to know your formulas. So if we're compounding it monthly or quarterly or daily, that formula is the amount after some time is the starting amount times 1 plus the interest rate in decimal over the number of times per year you're compounding to the number of times per year you're compounding times the number of years. So, how much is in the account after 10 years? If we're starting with 7,000, that's the starting amount, times 1 plus interest rate 4.5% or 0.045 in decimal, divided by monthly would be 12 to the 12 times the years, 12 times 10, which is 120. So the amount that would be there is 7,000, parenthesis 1 plus 0.045 divided by monthly 12, close parenthesis, to the 12 times 10. And there would be $10,968.95. So it was, that's this answer, $10,968.95. How long would it take to get to 10,000 if compounded quarterly? So quarterly to get to 10,000, so that would be after a while. Starting amount is still 7,000. And we're going 1 plus 0.045 divided by quarterly 4 to the 4t. Now if we can solve that, we'll have what it is quarterly. And to make these numbers not so big, we're going to divide both sides by 7,000, which reduces to 10/7. So I'm going to go to my calculator and my graph and clear, and put it in 10 divided by 7. And the other side will be parenthesis 1 plus 0.045 divided by 4, close parenthesis, to the 4x. And we're going to find out when they intersect. Zoom 4. There's one. The other one, it's going to be off the screen. Zoom 6 will probably make it on the screen. It's going up, hits, goes above. Second, calculate the intersection of the blue graph and the red graph, and my guess is 0, and it says no, it's 7.97 years. For the balance to grow to 10,000, starting with 7,000. How long for the balance to double if compounded daily? So now instead of 4, we're using 365, and we want it to be twice as much as it started, so we could put 14 and 7, or we could just realize this has to be 2 to double 7. So 2 would have to equal 1 plus 0.045 divided by 365 to n 365 times t. And when we solve for t, we've got it. So we're going to type in now, instead of 10/7, we're going to type in 2. And instead of 4's in here, we need to have daily, so that needs to be 365, and that 4 needs to be 365x. Now if I graph, it looks like it's off my screen. I need to look over further, so I'm going to change it to max x to be 20, and looks like they cross before 20 years. Second, calculate the intersection of the blue and the red, and it says it's 15.4. How much if the in the count after 10 years if compounded continuously. Well, the compounded continuously formula, which you should have on your note card, is e to the RT. So we want to know how much in the end. If we start with 7,000 as before, e to the interest rate in decimal is 0.045 t we're trying to find. No, we know in 10 years, so t is 10. So we have, our answer will be 7,000 startup money, e to the 10 times that is 0.45. 10,978, 819. 10,978, 19 cents.